Hi, my name is Jessica Hamrick, and today I'm going to be talking to you about inferring mass in complex physical scenes via probabilistic simulation. This work is in collaboration with Peter Battaglia, Tom Griffiths, and Josh Tenenbaum. So you may be familiar with the robot Wall-E. His job is to collect trash and to compress it into these trash cubes, which he then has to stack into these enormous towers. While this may seem like a simple task at first, it's actually much more difficult than you might think. For example, what if the cubes have an uneven distribution of mass? How does Wall-E know the correct way to stack them so that his towers don't topple over? In another example, what if the places where Wall-E collects trash are very unstable or precarious? How does Wall-E know to avoid these places so that he doesn't get injured? People reason about these types of scenarios every day, and often we don't even realize that we're doing so. Our ability to reason about these types of everyday physical scenes is what we call our intuitive physics, and we use it in nearly every aspect of our lives. On one end of the spectrum, we use our intuitive physics to safely navigate the world and to avoid dangerous situations. Just like this soldier, you would probably run out of this building in order to avoid being crushed by the falling debris. On the other end of the spectrum, our intuitive physics evokes a sense of wonder and awe when our expectations are violated, as in the case of this rock-balancing art structure, which, believe it or not, is actually stable. These are the types of scenarios that I'm interested in. How do people reason about the physical world? And, more specifically, how do people infer the parameters of physical objects? For example, this scene should cause you to make a strong inference about the mass of the forklift, the storage container, or possibly both. In order for this to be stable, the forklift must be very heavy, or the storage container must be very light. How is it that people are able to make such strong inferences from a static image? There is a long history of research studying how people make these types of inferences in physical scenes. However, researchers have often focused on the limitations of people's physical reasoning, assuming that they have little to no accurate knowledge of physics. For example, some have argued that people directly perceive mass, while others have argued that people rely on various heuristics and biases, such as that whichever object is moving faster after a collision is the lighter object. However, Sanborn, Mansinga, and Griffiths recently put forth a model which does have accurate knowledge of physics, but which is limited in other ways, such as by perceptual uncertainty. Their model was able to capture people's behavior in these classic tasks, suggesting that it's not necessarily the case that people don't have an accurate knowledge of physics, but that they may be constrained in other ways, such as by perceptual uncertainty. However, all of these previous lines of research have focused on how people reason in two-dimensional, simple scenarios. Yet, the world that we live in is a three-dimensional world, and is very rich and complicated. Research that I have previously been involved in has looked at how people reason about physics in more complicated scenes. For example, in these towers of building blocks. We asked people to make judgments about these types of towers, such as whether the tower would fall or what direction it would fall in. We then built a model based on the idea of physical simulation that was able to capture people's behavior in these types of tasks. The intuition behind the idea of simulation is that we can actually imagine what will happen when the tower falls over, and once we start to see the blocks fall, we can practically see the movement of them. So, from these two previous lines of research, we have that people can infer mass in simple scenes, and that they can make predictions in complex scenes. This leads to the next question of whether people can infer mass in more complex scenes as well. For example, if you see a tower with red and yellow blocks, and you're told that one color is heavier than the other, but not which color, can you infer which color is heavier? This is exactly the question that we asked people. We ran an experiment in which people saw a total of 40 trials, 40 different towers, in two possible orderings, and each trial was structured something like this. First, people saw the tower. We then asked them to answer the question, will the tower fall? After they answered, we showed them feedback. Either they saw binary text feedback, in which they saw just the words printed on the screen, will fall or won't fall, or they saw both text and visual feedback, where they actually got to see a movie of the tower falling or not falling. Finally, on some trials, we also asked people which color they thought was heavier. We additionally split people into groups based on mass ratio, which determined the feedback that they would see. For example, if yellow is heavier, then this is a stable tower, so people would see feedback where the tower does not fall. On the other hand, if red is heavier, then the tower is unstable, so people would see it fall. So, depending on the mass ratio, people saw different feedback which, ideally, would lead them to make different inferences about which color was heavier. This is indeed what we found. This plot shows the proportion of correct which color is heavier judgments after the 8th trial. You'll notice that the majority of people correctly inferred the correct color after only 8 trials. Here, 7 out of the 8 conditions are significantly above chance. This was the same for the rest of the experiment as well. Trial 40 looks essentially the same as trial 8. The one exception was one condition which never seemed to infer the correct mass ratio. Even at trial 40, they were still at chance. When we looked closer at this condition, we found that the first 2 trials gave confusing, anti-informative feedback, meaning that the feedback made it look like the actual heavier color was the lighter color. So, we think that people saw these trials, made the incorrect inference, and then got confused when later trials contradicted their initial inference. However, the corresponding visual feedback condition learned the correct mass ratio, even though they saw the same trials. We think that this is because there is more information present in the visual feedback. In addition to fall, not fall, people might be also paying attention to things like how many blocks fall, what direction they fall in, etc. So we think this extra information was enough to let people recover from the initially confusing feedback. Despite this one anomalous condition, I want to stress how quickly people seem to actually infer the correct mass in general. This is the same plot, but for trial 1, and as you can see, after only a single trial of feedback, many people had already inferred the correct mass. There seems to be some very powerful one-shot learning going on here. People are quite sensitive to the feedback that they're getting. So, we asked the question, can people infer mass in complex scenes? And the answer is yes, they can. The next question is, how? What is the mechanism underlying people's ability to make these types of inferences? We developed a model that combines the 2 previous approaches I mentioned earlier, the simulation-based physics knowledge that I have helped to study, and the rational approach to inferring physical parameters by Sanborn et al. I'll first describe how the simulation component of the model works. First, the model views the scene and forms an internal representation of the objects in the scene. However, it has some perceptual uncertainty, so when it perceives the scene, there is some noise in the localization of the objects. To give you a sense of what I mean by perceptual noise, I'm going to show you a short video of different perceptual samples the model might take. You can tell that they all come from the same original tower on the left, but that they are all slightly different. Okay, so once the model has drawn some perceptual samples, it runs these forward through a process of physical reasoning. This is actually a physical simulation, like that of a physics engine you might find in a video game. Finally, the model takes the final states from the simulations and compares them to the initial states in order to come to a decision on the physical judgment, such as will the tower fall. By considering all the samples, the model can approximate a distribution for the probability that the tower will fall. We will take this distribution now and embed it in our inference framework to allow for belief updating. As before, the model views the scene and uses its physics knowledge to compute the probability that the tower will fall given a particular mass ratio. It can then integrate over mass ratios in order to marginalize out that variable and give the distribution only over whether the tower will fall, independent of what the true mass ratio is. Next, the model produces a judgment of fall or not fall using this same distribution, engaging in a probability matching strategy. Finally, after the model observes feedback, it can evaluate the likelihood of that feedback under the same probability distribution for whether the tower will fall that I described before. It then updates its beliefs using Bayes' rule, giving a posterior distribution over masses, reflecting belief about which mass ratios are more likely. In order to see how well our model could explain people's behavior, we compared it with 2 other models. First, we computed the model fit for a model that guesses randomly. That is, it randomly says will fall 50% of the time and won't fall the other 50% of the time. Next, we computed the fit for a model that has knowledge of physics but doesn't actually update its beliefs. In other words, it ignores all feedback. Finally, we computed the fit for the full learning model, which has knowledge of physics and updates its beliefs about the true mass ratio after observing feedback on each trial. For each of these models, we evaluated the likelihood of people's responses to the question of, will it fall? If people are taking the knowledge they inferred about mass and generalizing it to other types of physical reasoning, then their responses to will it fall should change over time as their beliefs about the latent parameter for mass get more accurate. So, we should see that the learning model does a better job of explaining their judgments than the fixed or the chance model. If, however, people do not generalize their inferences, then we should see that the fixed model does better than the learning or chance models. So here's the chance performance. It is the same for all conditions because, again, it just assumes people guess will fall 50% of the time and won't fall the other 50%. Here's the fixed model. And here's the learning model. As we would expect, the learning model is better than chance at explaining people's behavior, except in the condition where people did not learn. In most conditions, the learning model is also significantly better than the fixed model, indicating that people's knowledge does transfer to other types of physical judgments. There were two other cases in which the fixed model and the learning model were equally good at explaining people's behavior, though both were better than chance. This shows that a model with knowledge of physics is most important in explaining people's responses. However, it also suggests that our learning model isn't a perfect account of people's behavior. There is something going on here that isn't fully captured by the learning model. In general, however, these results indicate that the learning model is at least a good starting point for explaining how people update their beliefs about mass over time, and how they generalize that knowledge to other types of physical judgments. So, all of these results lead us to a few questions that we want to focus on in the future. First, if it is in fact the case that people were sensitive to the anti-informativeness of the confusing feedback in that one particular condition, then we should be able to vary this information content and see systematic changes in people's responses. Relatedly, if it was the extra information in the videos that allowed people in the visual feedback condition to recover from the confusing feedback, then we would like to know which information they paid attention to. As I mentioned before, they could also be using features such as direction, the number of blocks that fell, etc., in addition to fall or not fall. Finally, people seem to be more sensitive to information that was present at the beginning of the experiment. An ideal Bayesian learner should not exhibit any order effects, so perhaps the primacy effect that we saw was a result of resource limitations or imperfect belief updating. So, in conclusion, we asked the question, can people infer mass in complex scenes? We determined that the answer is yes, and that they are very adept at doing so. People can infer the correct mass after only receiving binary feedback, and sometimes they can make the correct inferences after only a single trial as well. We developed a model which explained people's general behavior by combining approximate knowledge of Newtonian physics as instantiated in a probabilistic simulation, in a rational framework for inferring unobservable parameters like mass. So, to conclude, this work is an important step in understanding and explaining how people behave and reason about the physical world, and it provides a framework for studying how they learn about other parts of the environment, for example, other parameters like friction or perhaps different dynamics entirely. Thanks.